Hey everybody. Today we're going to talk about a lot of ideas, but primarily what we're going to be discussing is graphical analysis and how to use certain physical quantities in graphs to determine other physical constants. So I wrote that on the top here. We want to derive values from slope and the area under the curve of graphs. And what that means for us is I want to eventually be able to say, well, look at this graph. When you calculate the slope, that's a real physical quantity that might be actually useful. And when you measure the area under this curve, well, that could be another physical quantity that is mathematically useful. So I want to work on those together today. I want to talk about these ideas, but the big idea here is that we are going to be able to look at graphs and say, oh, now I know the distance this object traveled. Now I know the slope, now I know the velocity this object was traveling at. Now I know the acceleration of this object. And it's not necessarily going to be on your y-axis or your x-axis. It'll be calculated using your slope or using the area under the curve, this physical space here, breaking it into smaller shapes and finding those area values. Before we go into that, I want to make sure that we're comfortable with something we talked about in lab, which is the idea of base units. When we're measuring something in physics, we may have to plug it into an equation. If we are going to plug a value into an equation, we want to make sure it is measured in what's called a base unit. Some of these are quite straightforward. Distance, for example, our base unit is the meter. And the meter, which you can see here, is about 3.3 feet. About 3.3 feet. And 1 meter is going to be the equation, is going to be the value you want to plug into your equation, or X amount of meters, however many meters. So if you're given something in, let's say, centimeters, let's say you were given like 10 centimeters, well, you would have to convert that to meters by multiplying by 1 meter over 100 centimeters, and then you would get 0.1 meters, and that's the number you would use in your math. You would do like 3 times 0.1, not 3 times 10 centimeters. Make sure you're using these base units in your math work in this class. Time is another thing we're going to be measuring, and our time is going to be measured in seconds. So if you're working in hours, or if you're working in, let's say, kiloseconds, which is a prefix which would mean 1,000 seconds, you want to make sure you can convert to seconds before you do any other work. I am going to give us a chart on our reference table that has all of the metric prefixes and their conversion rates. Another common one here, and this one's a bit tricky, is the idea of mass. First of all, I want us to think of mass as resistance to change in motion, how hard it is to move an object. Something with a low mass is much easier to move than something with a high mass, like this entire building. It's much easier to move a truck than a butterfly because a truck has a very low mass. So I want to think of mass as resistance to change in motion. And mass is the only one that we're going to measure with a metric prefix. Mass should be measured in kilograms. So if you were given, let's say, for example, 200 grams, you would have to convert that to kilograms before you could actually do any math work. And you would get 0.2 kilograms here. So make sure this is the only one with a metric prefix in the base unit. There's a reason for that you're going to see when we do volume as well. But kilograms is the only one that has a metric prefix. So if you're doing equation work and it says, oh, we'll substitute in the mass of the object here, you need to make sure that you're working in kilograms, not in grams. I know it's a little counterintuitive, but there is a reason for it, and there always is a reason in physics. It might just might not be immediately apparent. These are base units, meaning you can simply measure them in and of themselves. For example, I can measure distance. I can measure the distance of this object. We don't need to plug that into an equation. It is simply a measurement. I can measure the mass of an object. If, for example, I want to take a kilogram, well, that's about 2.2 pounds on Earth. You might want to remember that. That's about 2.2 pounds on Earth. So a kilogram is roughly the weight of maybe a notebook or something else that's about 2.2 pounds. Maybe like a cantaloupe. A gram, by the way, it's about the mass of a paperclip. So I want to keep that in mind as well for metric estimations. Derived units involve math. A derived unit involves math. If, for example, we're talking about speed, right? To calculate speed, Well, you actually have to divide two quantities to find speed. And you might think about that on the highway. Think about that word miles per hour. What does that word per mean in math? The word per simply means divide. You're taking your miles, your distance, and you're dividing it per by your time in hours. Now in physics, we're not going to use miles per hour. We would do distance divided by time, and we'd get a value in meters per second. In meters per second. Because again, when you're working in your equation, you see distance, plug in meters. You see time, plug in seconds. So in physics, we're going to measure speed in meters per second. This idea of derived units, units that can come from mathematical operations, brings us the idea that a graph can have hidden figures within it. A graph can have hidden figures within it. Let's take a look at an example of that. Let's take this graph that I wrote right here. And this is a distance versus time graph. This is a distance versus time graph. I have time on my x-axis, I have distance on my y-axis. If we look at what this individual experienced, they went farther and farther away until after 2 seconds, they were at 4 meters. I'm going to actually mark off that note here as 4 meters after 2 seconds. Of course, you put your x value first. 2 seconds, 4 meters. Now I want to take a look at something here. What I want to look at is the slope from 0 to 2 seconds. I want to look at the slope here from 0 to 2 seconds. And let's see what that's going to give us. First of all, how do we calculate slope? It's change in y over change in x. You may have seen this as y2 minus y1 over x2 minus x1. Change in y over change in x. Let's look at the change in our y value here. The change in our y value goes from 0 meters to 4 meters. We have a change in y of 4 meters. What's our change in x? Well, we go from 0 to 2 seconds. So we have 4 meters over 2 seconds. We get 2 meters per second. Change in y over change in x gave us 2 meters per second. What am I measuring if I'm measuring in meters per second? Well, let's go back. It's not distance anymore, because that would just be meters. It's not time anymore, because that would just be seconds. Those are easily read on our x and y axes. Yes, it went 4 meters. Yes, it went 2 seconds. But the speed of the object is what we're given here. 2 meters per second is the speed of the object. So in a distance versus time graph, your slope is speed. Because change in y over change in x gives you the change in distance over the change in time. And change in distance over change in time is speed. You could also see another slope here. Let's take 2 seconds to 4 seconds, for example. 2 seconds to 4 seconds. What is the slope here? Well, look, that's a flat line. The slope here would be 0. And again, it would be 0 meters per second, because you're measuring speed, change in y over change in x, 0 over 2 seconds. So slope here was distance over time, measured in meters per second. Is slope always going to be distance over time, meters per second? No. Slope is going to depend on what you're actually measuring on your graph. Take a look at this graph, for example. We have force measured in newtons on our y-axis. We have distance in meters on our x-axis. What is our slope going to be? Well, we do change in y over change in x, and that's going to be force divided by distance. It would be newtons per meter. Now, does that have a physical significance? Actually, no. Newtons per meter is not a quantity that we're going to use in this class. But the point I want to raise is it doesn't matter what's on your y-axis, what's on your x-axis. If you take this value and you divide it by this value, that's what your slope is measuring. So slope is always change in y over change in x. Those y values could be physical quantities like distance, and those x values could also be physical quantities like time. Similarly, the area under the curve of a graph could also have a physical significance. Let's take a look at a different scenario here. Now I'm giving you a velocity versus time graph. Notice how this graph is different from the first one. This graph gives velocity on the y-axis and time on the x-axis. Of course, the slope still has physical significance. If I took, for example, the slope here from 0 to 3 seconds, if I took the slope here from 0 to 3 seconds, Well, I would get change in y over change in x, which here would be from 0 to 15 meters per second over 3 seconds, which would give us 5 meters per second, which is 5 meters per second squared. If we have 5 meters per second squared, well, what does this measure? This is actually going to be our unit for something called acceleration. Acceleration, which is change in velocity over change in time. But you already knew it was going to be change in velocity over change in time for our slope, because we just talked about how change in y over change in x is slope. Here on our y-axis, that's velocity. Here on our x-axis, that is time. And velocity over time happens to be acceleration. Now, I don't expect you to know acceleration yet, but I do expect you to be able to identify, oh, change in y over change in x, I have to divide my y-axis by my x-axis. Velocity over time. Change in velocity over change in time. By the way, this triangle here, that means, that delta symbol, that means change in. So that's that triangle there, it means change in. It's like final minus initial. Let's take a look at another property of this graph. The area under the curve, and by that I mean the area between the actual lines and the x-axis. The area under the curve also has a physical significance. Let's take, for example, this little triangle here. And I'm going to sketch out this triangle. I'm going to draw a line down right here. And I want to look at this triangle together. And if you look at this triangle, I'm going to redraw it over here actually. If we look at this triangle has a height of 15 meters per second. So we have 15 meters per second as our height. It has a base of 3 seconds. I could find the area inside this triangle by doing 1/2 base times height, which here would be 1/2 times 15 meters per second times 3 seconds. Take a look what happens when we multiply this out. Over seconds times seconds, they cancel. You get 1/2 times 15 times 3, and you should simply get here 22.5. And what's our unit going to be? Well, seconds canceled because we did meters per second times seconds, and those canceled. Now we're left in meters. So what did this area tell us here? What is measured in meters? This area under the curve is the distance the object traveled. The distance is the area under a velocity time graph. Under a velocity time graph. So our distance is the area under the curve because we're multiplying velocity times time. Look for the units to cancel out every time here. Let's add even more to this. What if I wanted the whole distance it traveled in this entire time? Well, look what shape we have here. This is a rectangle. And I can calculate the area of this rectangle. It is 2 seconds long, 3 to 5, 2 seconds long, and it is 15 meters in height. A rectangle is simply base times height. So 15 meters per second times 2 seconds, and you get 30 meters. So now we have 30 meters here, 22.5 meters here. The total distance traveled is 52.5 meters. That's our total distance traveled by this object, 52.5 meters. Long story short, change in y over change in x is your slope. Sometimes that will give you a derived value, like velocity or acceleration. Y times x is your area under your curve. Sometimes that gives you a value. Like here it gave us distance. Velocity times time gives us distance, because meters per second times seconds cancels out. And again, that's true of any graph. Like here, area under the curve, and make my triangle, what's it going to be measured in? Well, we have change in y, we have change in x, you multiply them. We multiply our y value times our x value. So here it's force times distance, and force times distance actually happens to be a real one. Newtons times meters happens to be a real one. Newtons times meters is going to be something called a joule, which is how we're going to measure energy or work. Again, you don't have to know that yet, although some of my AP students might from last year, but you do need to realize anything on this graph, y over x or y times x, can have a real physical property. These three base units, meters, seconds, kilograms, those are going to set us up for the first 6 months. We're going to learn some more later in the year, but most everything is about, for the first half of the year, is converting to meters, seconds, or kilograms, plugging it into equations, finding the value I want you to find.